So our previous lecture ended up at the definition of linearly independent set of vectors, and I have finished by giving an example. Okay, so I would like to recap the definition of linearly independent set, that is a set of vectors v1, v2, vn. So recall that a set of vectors v1, v2, vn in a vector space v over a field f is called linearly independent if is called linearly independent if for any choice of scalars alpha 1, alpha 2, alpha n such that alpha 1 v1, alpha 2 v2, alpha n vn equals to theta. Now that would imply that alpha 1, alpha 2, alpha n, each one is 0. So this is the definition of linearly independent set of vectors over a field F. Okay. And I have also specified that no vectors in a linearly independent set can be a zero vector. Okay. Okay. Now it should be remarked that the linear dependence in a vector space not only depends on the vectors. So it should be remarked that linear dependence in a vector space not only depends on the vectors but also depends on the field. So linear dependence not only depends on the vectors, but it also depends on the field that we have considered, over which the set V forms a vector space. For instance, if we consider the set of all complex numbers, suppose we consider C, V equal to C, over two fields. One is the field of reals and another is the field of complex. Over two fields. One is the field of reals and another is the field of complex. In both the situation, the set of all complex numbers forms a field, forms a vector space over both the fields, let's say the field of reals and over the field of complex. Now let us consider two vectors in C, in the vector space C. So let us consider two vectors. Suppose one is I and another one is -1. Now over the field of reals, these two vectors are linearly independent. But over the field of complex, this set is not linearly independent. It is linearly dependent because we can write it down as 1 v1 plus I v2, and that would be, so 1I plus I minus 1. So it is I minus I, and this is 0. But the scalars are non-zero scalars. So thus one can be represented as a linear combination of the other, the scalar multiple of the other. And that means these two vectors are linearly dependent over the field of complex. So v1, v2 is linearly dependent over C. But over the field of reals, they will form a linearly independent set. Just by equating the real and complex part on both sides. That is, if over the field of reals, if you can consider the linear combination alpha 1 I, alpha 2 minus 1 equals to 0, then this will be, so minus alpha 2 plus I alpha 1 equals to 0. So now equating the real part and imaginary part of this complex number with the right hand side, then you will get alpha 2 is 0, alpha 1. So this means over the field of reals, these two vectors forms a linearly independent set of vectors. So this shows that the field over which the vector space has been defined is very crucial, is very important, and we must stress on this, on the character of the field over which field we are considering the vector space. That is very important. Okay. Now I would like to call a theorem which will give you an indication of importance of linearly independent set of vectors. And why these set of vectors are very much important in vector spaces. The reason is that now if we consider a vector space V over a field F, so let V be a vector space over a field F, and suppose V1, V2, Vn be a linearly independent set of vectors in a vector space V. Then every vector, just look at this conclusion, then every vector in the linear span of these vectors V1, V2, Vn. So every vector in the linear span of these vectors can be uniquely expressed as alpha 1 v1, alpha 2 v2, alpha n vn, where alpha 1, alpha 2, alpha n are unique scalars. Now one may say that any vector in the linear span of this set v1, v2, vn, so by definition it can be expressed by a linear combination of the vectors v1, v2, vn. So there is nothing new in it. But whenever you are considering a linearly independent set of vectors, then this representation is unique. You cannot represent the same vector in more than one ways. So this is the importance of why we are considering linearly independent set, because you can represent the vector in the linear span of v1, v2, vn uniquely as a linear combination of v1, v2, vn. So this is important, that the representation of each vector is unique. You cannot represent a vector in more than one ways. Okay. And the proof is very simple, because suppose that V be a vector in the linear span of this. Okay. Now, by the definition of linear span of vectors, you can write V as a linear combination of V1 with Vn. So then there exist scalars alpha 1, alpha 2, alpha n belongs to F, such that V will be represented as alpha 1 V1, alpha 2 V2, alpha n Vn. So you will always have this representation because you are considering a vector in the linear span of the vectors V1 with Vn. But we have to show that this representation is unique. So that means the scalars that we have considered for the representation of V must be unique. So to show this uniqueness, we need to consider another representation of V. To show this uniqueness, let V will be represented as a linear combination of V1, V2, Vn in another way. Suppose the scalars are beta 1 V1, beta 2 V2, beta n Vn. Okay. So what will happen now? So V has two representations, so we may equate them. So alpha 1 V1, alpha 2 V2, alpha n Vn equals to V, and V is equal to again V, beta 1 V1, beta 2 V2, beta n Vn. Okay. So now, just by doing simple algorithms, so let alpha, so this implies that alpha 1 minus beta 1 V1, alpha 2 minus beta 2 V2, alpha n minus beta n Vn equals to theta. Now we need to use the fact that V1, V2, Vn are linearly independent. So since the vectors V1, V2, Vn are linearly independent, so we must have alpha 1, beta 1, alpha 2, alpha 2 minus beta 2, alpha n minus beta n. These are all zeros plus, which implies that alpha 1, beta 1, alpha 2 equal to beta 2, alpha n equals to beta n. So these scalars are same. So this proves that the representation of V is unique. Okay. Now, suppose in a vector space V, you have n many vectors, say V1, V2, Vn. Now the next result, although it apparently seems to be very technical, but it has some important consequences and which build the very basic foundations of the subject. Although the theorem is very technical. So the statement of the theorem is, suppose we are considering, we consider a vector space V over a field F and let V1, V2, Vn be n many vectors in the vector space V. Then two possibilities may occur. Number one, so I should write down the theorem. So let V1, V2, Vn are vectors in a vector space V. Then what will happen? Then either these vectors are linearly independent or some vk is a linear combination of the preceding vectors. That is V1, V2, Vk minus 1. So either the vectors are linearly independent or some vector Vk can be expressed as a linear combination of the preceding vectors. That means the vectors which are coming before Vk, that is V1, V2, Vk minus 1. So why does such thing happen? Because the first case is, if they are linearly independent, then we have nothing to prove. So we must assume that these vectors are not linearly independent. And for this reason, suppose that alpha 1 b1, alpha 2 b2, alpha n bn equals to theta for some scalars, alpha 1, alpha 2, alpha n. Okay. And we need to consider one more assumption, which is alpha i's are not all zero. Alpha i's are not all zero. Okay, these alpha i's, the scalars are not all zero, since the vectors are assumed to be linearly dependent. Now, it may happen that it may happen that after kth term of these representations, the scalars are 0. All the scalars after kth term are 0. Then we may define a largest positive integer k. So k is the largest positive integer for which alpha k is not equal to 0. And all other alpha k's are 0 after the kth term. That is, alpha is a 0 for all I greater than k. And so we have, using the above representation, so the remaining sum will be alpha 1 b1, alpha 2 b2, alpha n here, alpha k bk, sorry, alpha k bk equal to theta. Because after the kth term, all the terms are 0. Now, since what we have defined for the kth term, that is alpha k is not equal to 0. For this reason, since it is a scalar, non-zero scalar, so it must have a multiplicative inverse. So one may write down this equation as, so it is alpha k bk minus alpha 1 b1 minus alpha 2 b2 minus alpha k minus 1 bk minus 1. Now, since alpha k is non-zero, so we may multiply alpha k inverse scalarly with this vector, and then we have this alpha k inverse alpha k bk, and on the right hand side we will have alpha k inverse alpha 1 b1 minus alpha k inverse alpha 2 b2 minus alpha k inverse alpha k minus 1 bk minus 1. Sorry. Okay. bk minus 1. Yeah. So that means this part is 1, so 1 dot bk is bk. So bk has been represented as alpha k inverse alpha 1 b1, this is a scalar, minus alpha k inverse alpha 2 b2 minus alpha k inverse alpha k minus 1 bk minus 1. And this shows that the bk is a linear combination of b1 b2 bk minus 1. Okay, so this proves the theorem. That is, either the set of vectors are linearly independent, or some vk is a linear combination of the preceding ones. That is v1 v2 vk minus 1. Okay, and with the help of this theorem, we will at once have the following corollary. What is the corollary? The corollary says that if we assume n many vectors, suppose b1, b2, bn are n many vectors, in a vector space V, and W has been defined as the linear span of the vector v1, v2, vn. Yeah. That means it is ls of vn. Sorry. Now if amongst these n many vectors, if v1, v2, vk's are linearly independent, let's look at the conclusion. That is, if v1, v2, vk are linearly independent. So amongst the n many vectors v1, v2, vn, if v1, v2, vk are linearly independent, then there exists a subset of v1, v2, vn containing v1, v2, vk, consisting of linearly independent subsets whose union span is W also. Whose linear span is W also. So let us write down the statement. So if v1, v2, vk are linearly independent, then there exists a subset of v1, v2, vn containing v1, v2, vk. So containing v1, v2, vk and consisting of linearly independent consisting of linearly independent elements whose linear span is W also. So among the n many vectors, you may construct k many vectors. Among the n many vectors v1, v2, vn, you may construct v1, v2, vk consisting of linearly independent set of vectors whose linear space is W also.